I'll just ask you later.
Okay, so we're going to continue on with atomic models. We've talked about quite a few people up to this point. Quick review. Who was the first guy? Lucipus. What is? Give me the highlights of him.
He started the whole idea.
Started the whole idea. Okay. What else? Anything else that's important about him? No experiments. Yes, very important. His model looks like what? Oh yeah, solid sphere. Okay, then we came along Democritus. What was Democritus' relationship with Lucipus? Student. Okay. And Democritus did a few other things. Still was what? Still was Greek. Still didn't do what?
Experiments.
Okay. But he's credited with what?
Naming the atom.
Naming the atom. And his model is only slightly different.
The heat surface beneath.
No, that's Dalton. The Bishop model.
Oh, it's the Bishop.
Right? The Bishop model. Okay, and catch some big fish with that thing, right?
Right.
Next came John Dalton. Now he's the first guy to do what?
Experiment.
Okay? Then he also did something that may not be as obvious to you guys, was how he used the law of definite composition to assign relative masses to things. And what he noticed is that atoms had different masses. And he attributed those masses, or he explained those masses in his model with what?
Heat bubbles.
What did you say? Heat bubbles, right? Or heat envelopes is what he would call them. The difference in the masses of the atoms was due to this like theoretical heat bubble. Okay? Yes? Yeah. Then along came J.J. Townsend. He's known for what? Coming up with the plum pudding model, what was discovered when he did that? The electrons were discovered. We're not going to get too crazy into how he did that. Okay, then Ernest Rutherford had an experiment known as the gold foil experiment, and he discovered what? The nucleus. He shot alpha particles through gold foil. Most of them went straight through, so he discovered not only the nucleus, but also that most of the atoms made up of empty space. Okay? And it was like 10 years later he discovered the protons. Yes? Alright, so we are going to get to Mr. Chadwick today. I'm gonna name my next son Quantum. Quantum Kramer.
You call him
Quanti or Quan? Quan Kramer. QK.
It's like a really cool like wrestling.
Or I can name his middle name like Andrew, and we call him Quack. Even though there's no U in there, but you get it. Yeah. How would you say that without the U?
Quack.
Cack?
Yeah.
So what up, Cack? Woo! Alright. Here's what Chadwick did. And this is one slide for this dude. Probably check. Maybe irritation, harmful if swallowed, avoid breathing mist vapors or dust.
That sounds
We'll wait
great.
till the night, eh?
So basically just dumb. Just
Ingestion, if conscious, induce vomiting.
Oh, okay.
Okay.
That's
We'll
not
wait to open that one.
I like vomit.
Ammonium chloride may cause irritation, harmful if swallowed, avoid breathing dust. Use an adequate ventilation.
Why by me?
Oh, here. Just gonna open it. Gotta have some adequate ventilation.
Yeah.
Who could open that one? That means when the ventilation is gonna go like
You
this.
just do it outside.
That's smart.
Harmful if swallowed, avoid breathing mist, vapors, okay.
Can I move back there, actually?
This
I'm
guy's
not
Kidding.
This one's not so bad. Do not breathe fumes, that's it.
Because if you breathe the fumes, you will grow a third
A
arm.
little bit. This stuff is, I'm just joking. That stuff is really not that bad.
Then your back arm.
I mean, it was on my
Back of the
finger. It's
head.
not that big of a deal. Okay? So, here's what Chadwick did.
Is also.
That's third arm on your back.
Hey, keep going. In order to get to some of the cool stuff, we need to get through this stuff. I'm saying this stuff is cool.
Totally butchered
I always spell neutron wrong. It's neutron.
Yes, I would spell like
always wrong.
neutron, so I did
Wrong.
do this.
And then he nucleus.
Nucleus.
All right, here's what Chadwick discovered. He discovered the neutrons. Okay? He also noticed that these neutrons were about as big as a proton but didn't have charge. Okay, now they were in the nucleus. Here's essentially what he did for discovering the neutron. I'm going to just do it really quickly. He took positive and negative plate, like a magnet. Think of it like a magnet. Okay? He accelerated positive ions. So he essentially shot positive ions through the charged plates of one kind of atom. And he noticed that when they went through the charged plates, they bent. Well, they shouldn't bend towards the positive. That doesn't make any logical sense if they're positively charged particles. So we'll bend them this way, right? That makes sense. If it's a positively charged particle, it's probably going to be attracted to the what? Negative, okay? So he was expecting, let's say this was just a bunch of calcium cations, and he would expect all those calcium cations to bend exactly the same because they would bend exactly the same because their mass was the same. Okay? For example, it would make more sense that charged particles would bend more the lighter they are, and would bend less the heavier they are, due to inertia, essentially. Okay? And what he noticed is some of the calcium cations bent more, some bent less, which led him to believe that they had different numbers of neutrons in them. And we'll get to isotopes later, okay? But he realized we know protons, we know electrons, and we know they have the same amount of both because it's neutral. Where in the world does this difference in mass come from? It had to be something else in the atom, which eventually they discovered that the neutrons. Questions? I'm not going to make you remember all that. Just kind of need to kind of think about how we discovered it.
That is model look like
He doesn't have a model. Okay? He doesn't have a model. He just maybe added to Rutherford's model. Mr. Bohr has a model though. Mr. Robert Boyle.
That's more like Bohar.
And his model's not the boring model.
Bohar.
Really bad.
Shit.
What? Is this what we're doing?
We'll open up this one
It says fireworks. I'm scared.
too. Yeah.
you go to open now.
No, not tonight. I played basketball after Church and Grace with a bunch of guys.
Oh,
I'm slightly concerned.
We are like
It says
someone's
fireworks.
And then, what we're gonna do is we're gonna light on fire. and
Do
make
you know there's a lot of chemistry involved in fireworks?
Yeah. Not my
Okay? So what Bohr noticed, okay, he noticed that if you gave certain things energy, you notice different colors a lot of times that got emitted. Okay? So I want to make sure you get it all in before I explain like the big picture. Yeah, so what I'm essentially going to do is I'm going to have you get all of the information about Bohr. I'm going to summarize all that Bohr did, and then I'm going to show you some cool things, and then we'll move on. Cool? Cool. We'll touch on this stuff a lot more in chemistry. We're just kind of setting a little foundation here so that when you take chemistry, we can go deeper into this concept. Because in chemistry, we identify where every electron in every atom is located, what orbital it's in, what sublevel it's in, what energy level it's in, all of those things. We won't do that today. Okay, I'm just going to move on to the next slide when we're done with this. So we get out, like I said, we're going to get all the notes, and I'm going to come back and talk about the whole Bohr idea. Yes?
Okay, so what happens if you shot atoms or you just go through?
So, remember he shot through a thin layer of gold. The thicker stuff you are, the more you could have like nucleuses stacked behind each other. You see what I'm saying? And so you probably have more ricocheting going on in that context. But yes, it would at least for sure go to the beginning part. It would go through the beginning part of your atoms. Yeah. That was a little bit trickier to, you see what I'm saying though? Like the thicker something is, the more you've got layers of nucleuses that you have to go through, so it becomes less likely to go straight through. Okay, so I'm happy to get this next slide in, the following one, and then we will put it all together. You want to go click to the next slide? One more. All right, there's your last slide here. That one, I don't know. Maybe I don't want to do that one. That one does have a few more health concerns. We want to do that one.
Safety walls.
No, I'd probably be fine.
Hazmat suits.
We probably would be just completely fine, but I have enough to show you without having to open up one Right? The only thing that's bad is if you sit right underneath it and start snorting, essentially.
Oh, wow.
Like, I mean, you know, if a little bit gets in the air and you smell it, you'll be completely just fine. Okay? So here's what happened. Mr. Bohr, and this is not in your notes, and I want you to put it in right now. Here's what Mr. Bohr is famous for discovering. That there are energy levels within an atom. Okay? You want to write this in your notes. Now, Mr. Bohr is famous for discovering the energy levels in an atom. Get that? Mr. Bohr is famous for discovering the energy levels in an atom. Okay. This is Bohr's model. Why don't you write that in too? Well, let me see if there's just a lot of slide that has a better picture of it. Yeah. That was, no, you don't have to do that much. Just do this. This is fine. That's a little expensive. That one's what his model of krypton would look like because it has a lot of protons and electrons. This would be the model of helium. It only has 2 protons and electrons. Okay, so here's what he did. He discovered that there were varying energy levels within an atom where the electrons were held. So this would be like the first energy level, second energy level, third energy level, fourth energy level. And here's how the energy levels worked. Okay, as the energy levels got bigger, the electrons spent time further away from the nucleus. Okay. They also had much more energy in order for them to get that far away from the nucleus. So the electrons in this energy level have much more energy than the electrons in this one, and so forth. Does that make sense? In order to get away from the positively charged nucleus, they have to have more energy to do so. Make sense? Yeah. Okay. Where was I? Okay, so he discovered these energy levels, and he noticed something due to fireworks and other things, that what could happen is that, let's say we got energy increasing here, and let's say that's like the first energy level, and that's the second energy level, and that's the third energy level. Electrons in each energy level could get excited. What that means is that if they get enough energy, they can actually jump an energy level. Okay, so if I got an electron here and I give it a bunch of energy, it could jump up to here, it could jump up to the third energy level, and so forth. Well, the higher energy electrons are, the more unstable they are. Okay, think of it this way. Low energy means stable, high energy, unstable. Go into a room with a bunch of little kids, high energy, not a stable environment. Go into a room with a bunch of old people, low energy, pretty stable environment, until someone dies.
Oh.
Okay.
That's okay.
Morbid. Okay. Anyway, so here's what he noticed: is that electrons would jump energy levels. They'd be like, "Hey, I'm not stable. I don't like this." So what they would do is they would go back down, but they had to give off the energy that they gained, and they did it in the form of light. Do you know fireworks, the different lights that you see are the result of electrons getting excited to certain energy levels and then going back down to their stable state and giving off light energy. The color of the light depends upon what energy level they jumped and wavelengths that they emit light at, things like that. That's much more complicated. Okay? But that energy, the light energy that we see, comes from excited electrons dropping back down to their original state. Let me show you. Well, we are going to, because obviously you're going to give energy to a firework in the form of boom, right?
Haha. Boom.
It's gonna be loud.
No, this is not going to be loud. It's just going to be pretty.
Oh, this one was different.
Now this guy's you're gonna die.
Oh, where the
Is that
fire
helium?
changed
Yeah.
the color.
What's the matter?
Whoa, fire.
Oh,
We did this last.
Did you?
Fire.
Kinda. I just want to see it again.
With Mr. Fisher?
Yeah.
Mr. Fisher.
Ah,
That's
what the context was he talking about it
We were
in?
talking about salt.
Oh, I guess these are all salts. But he didn't tell you why they made the cool colors they did?
No.
It was fire.
This one's supposed to do this.
This looks fun. Well,
Smells like fire, yes.
Alright, so we'll start with the first guy. Okay, that one's not very cool.
That one sucks.
It's the same color as the actual
Flame.
What's the difference?
Don't worry, it gets better.
Oh, green.
Oh, that's so cool.
Like,
I
it's
just
just
saw
like
it
it.
before, but it's just so cool.
Greenish. It's like
That's right, it's
liquid.
green. Oh, wait a minute.
Yeah. So this particular guy emits energy in the form of a greenish color. It's turning blue because it's running out and it's mixing with the orange.
Steven sees pink. That's cool.
How do you see
See a little pink on the
He's
inside.
kind of
He's
colorblind.
colorblind.
He's kind of colorblind, so he sees pink.
Look at that, it's burning blue. Pretty cool.
Pink.
Let's see what other colors we have.
I'm not sure one of these are actually.
Oh no, an ash. Yeah.
Oh, are you telling me this is also one of those dull, boring ones?
Look at the dangerous.
orange?
I mean, it's kind of doing something.
Whoa, it turned orange.
What is that? Ammonium chloride, boring. I just
Well,
grabbed
I
the
guess
quick
it's
computer
Epsom
time.
salt.
I might actually have to pull out the one that's deadly.
Oh, let's go back there then because I'm scared.
Just don't inhale it, Jay. You'll be
Try
fine.
this one, this one's pretty good.
Snort it.
Oh,
That.
Yeah.
It's red.
Oh, didn't want to do that.
I really did not see.
Well, I just let a whole bunch go right in the middle of it, so it's gonna just start getting pink on its own.
At least the pink is.
Ooh,
that's cool.
it's like a magenta color.
It's so pretty.
Okay, so the difference in colors have to do with the chemical makeup of each individual compound and how its electrons are getting enough energy to jump an energy level higher or a couple energy levels higher, and basically what energy levels they're jumping from and to, and what determines what wavelength of light they give off. Okay? I don't know.
Yeah, do it.
Yeah,
do
yeah,
it.
do
Do
it.
it. It's worth it. It's worth it
Do
if the
it.
poop is
Do
wrong.
it.
Don't do it. It's
What
worth
is
it.
What did you say?
It's worth it if we have to throw up and poop the rest of the week.
I'm actually gonna move it that way. So
Same shit.
have fun. I'm actually gonna back up.
Changers.
I know.
No chicken.
Fuck. You're already that far away.
Well.
Well, I didn't want to get that all over, but that's
That's red.
Oh my god.
Whoa, that's awesome.
Am I getting
I wonder if that's where they get the like sparkly.
Yeah, that's what I was
Yeah,
wondering.
what color?
That's just.
It's not a color, it's like just like
So wait, that's
It's like doing like
fireworks?
sparkly.
That's the one that you know.
Shane,
Sounds
do
like
the firework
sparkly.
noises.
I'm not sure. It must not be that bad for you if they put it in sparkles.
No.
Let's just assume that it's a sparkler. So
Maybe that's the stuff that they covered.
Alright, I think we've seen it.
Sparklers. I can make the noise one of those really loud screeching fireworks.
Alright, so we get the idea here that Bohr really his main contribution is that realizing that electrons' location is not all in one predictable spot. they're kind of No, I just had some mucus. So he came up with these varying energy levels and realized that get some more air moving in here.
What is that supposed to do?
He's wafting the smell away. And so he came up with the fact that these electrons are in a predictable location. They're at varying energy levels away from, that's cold.
No, it's better. Do it on me.
Face it towards me.
Yeah, face it towards me.
Just face it. Right, right. Yes.
Okay. Now, here's what was one big mistake that he made. He thought that these energy levels were like these big spherical circles, and that these electrons kind of orbited the nucleus in these energy levels like planets orbit the sun. That's what he thought. Okay? Now, they don't actually orbit like that. It's a way more complicated process than simply just orbiting like planets orbit the sun. Okay, and we'll find that out as we get to a higher level class. We'll introduce it today, but really, he did not come up with a correct a model that perfectly described how electrons orbited. Last model, quantum model. So it turns out the path that the electrons take when going through and when moving within the atom is a lot more complicated than what Bohr thought. Okay, so the quantum model is the model that we view as the correct model today. And really the only difference is we've discovered the protons, the electrons, the neutrons, we've discovered where they're located. We just need to fix a little bit about how the electrons moved within the atom. Okay, so kind of where the electrons were located, but just very slightly. Okay? Believe it or not, there is a principle. I'm going to get really deep with you here for a second. Okay, you probably won't understand a word I say, but I want to at least say it, just so that if when you get to the higher level classes, you'll have heard it before. There's a principle that states that it is impossible to know the exact position, momentum, and energy of an electron at any given time. Like mathematically impossible. I don't know the mathematical results or how to do the mathematical stuff, but these really super smart scientists realize you cannot predict where an electron is going to be at any given time. Impossible. Okay? However, what they could do is they could use probability, and they could describe the likely probability that an electron would be in a certain region. That region they called an orbital. Okay? So we don't know exactly where any electron is going to be in any one atom at any given time, but we do have a probability that it's going to be in a specific region within a specific energy level. Now, where within that region exactly, we don't know at any given time. But we know it's going to be likely in this one region. Okay? And there are 7 energy levels, and you'll learn this when you take chemistry. First, second, third, fourth, fifth, sixth, and seventh. Each energy level has different sublevels. And each of those sublevels have different orbitals. Okay, so it's actually far more complicated than what we're getting into now. Okay, but when you guys get a little bit older and take a little more upper level classes, we'll talk much more about all of those things. All I want you to know now is that the electrons are in these regions called orbitals that are really just probable locations. And I don't know.
How are we supposed to know that?
That's not a great model. What I would here's what I would do. Here, I know this is going to be kind of. First of all, this is a 3-dimensional model, right? So it's very difficult to draw a 3-dimensional model on 2-dimensional paper. Where the heck is mine?
Last time
I drew it.
you put it in
I got
the
it.
You know, you're a smart girl, Carly. So if I were to draw the model, I would have my nucleus in the center with your positive protons and your neutrons, and then here's what I'm going to do. You guys don't know this, but there's an s orbital, and it's a sphere actually. Then there are p orbitals that actually look like dumbbells. Now again, think 3-dimensional here. There'd actually be a p that would go into the page and out of the page, but the electrons are in these, these orbitals. What's that?
Yeah.
I'm only showing you 2 sublevel worth of orbitals in 1 energy level. I mean, if you got to overlap 7 energy levels worth of many different sublevels. Okay, I'm just kind of giving you like an outline version of this. I think that is it. So there would be what it would look like if you added them all together. And that's it.
Yay!
We're done, so perfect timing.
I'm so hungry. It is.